Okay, so in this session we are going to really spend some time understanding the notion of high intensity physiology. So this is really the physiological responses to exercise in excess of the VO2 max. The so-called sprint-based or power-based exercise, where we're working at nominally high exercise intensities. In other words, we're working under conditions where predominantly the energy is being provided from anaerobic metabolism through the high energy phosphates or through substrate level glycolysis. And what we're going to do is we're going to spend some time understanding the way in which those energy pathways interact with each other, the way in which they provide energy for the muscle to do work, but also understanding about the relative contribution of aerobic energy under high intensity conditions. And then we'll get into an understanding of what happens when we put multiple trials together and what the effects are in terms of multiple sprint-based exercise. So to do that, we've got to start off by reviewing the relative contributions of substrate metabolism. And we're going to look at that in relation to short-term exercise. So this will really follow on from work that you've done, for example, in exercise physiology modules, and some of the work we've covered in such modules as physiological profiling for endurance. Then we're actually going to see what happens. We're going to look at those kind of in isolation. Then we're going to see what happens to those energy pathways and the substrate metabolism under conditions of high intensity exercise. So this is, as I say, conditions where the intensity is in excess of the VO2 max. And we're going to understand how they interact with each other. So rather than viewing them in isolation, which we'll do in the first part of this session, we're now going to see how they interact and work with each other to give us energy provision for the muscle to do work. And then we're going to get to understand the role for oxidative metabolism doing high intensity intermittent exercise, which is really the part that a lot of people I think tend to forget about. Most people think about anaerobic substrate metabolism, they think about the high energy phosphates, they think about glycolysis, but forget that actually there is a large contribution under these high intensity conditions from aerobic metabolism, and particularly where we try and go for quite long duration based intervals. But even if we've got quite short intervals, I mean there's data that came out back in the 80s from people like Greg Gaetanos, and even more recently from people like Ralph Benneker, which demonstrated that even if you're exercising for about 10 seconds, there's quite a high aerobic contribution to energy provision. So we'll start off with kind of an overview. Now this is from a very nice review paper that was published in the European Journal of Sports Sciences some years ago. But it's quite useful for us in a number of levels. You can see that on the left hand side we've got the system, and we'll come back to that in a moment. We've got the substrata, so that is the substrate. Then we've got the relative power. So this is the power which is being measured. The units here are millimoles per kilogram per second, measured in wet tissue. And then we've got the capacity, in other words, how much of this do we have available to be able to do work. So the first thing we're going to do is just deal with something which is a little bit of an issue with this slide in many ways, which is this terminology, which is alactic and lactic. Alactic and lactic is old terminology in many ways, and it's terminology you'll still see, and it really came about from some publications that came out in the 80s, which were trying to, I suppose, distinguish between energy that comes from high energy phosphates and energy that comes from glycolysis. And the way they did this was by stating, well, glycolysis, the net product, you can in fact see it here on the substrata, the net product of this is not only ATP energy provision, but actually it's also the fact that we get lactate being produced. So they referred to that as the lactic energy generating system, and then they referred to ATPPC, where it's the high energy phosphate, as alactic, implying that there is no lactic acid or lactate production associated with that pathway. Well, in real terms, that is correct. I mean, if you were looking at those in isolation, PCR as a metabolic process and the conversion of splitting a PCR to generate ATP through the donation of the free phosphate to ADP doesn't in itself yield any lactate. The issue is that you're kind of implying and forming an opinion, which is that they're in isolation. They're not in isolation, and so we never really get a true alactic condition. It doesn't really happen, because as you probably recognise that even if you're doing a block of high intensity work, there'll be a relative contribution from the ATP-PC, there'll be a relative contribution from the substrate level glycolysis, and so on. So the alactic and lactic terms are terms I think I would advise you not to use, because we don't really have a condition of alactic metabolism, that is in the absence of lactate. So moving away from that, let's just deal with what we can see. So you can see the substrata. So under this alactic condition, that's ATP, it's PCR. We're going to go through this in more detail in a moment. But the splitting of the PCR leads to production of ATP, and we get a power output of about 3 to 6 millimoles per kilogram per second. Now don't worry about the units per se, think about the numbers. So 3 to 6 millimoles per kilogram, but the capacity in the muscle is about 20 to 25. If we move now to deriving energy from glycolysis, so the 10 stages of glycolysis ending up with the production of lactic acid, notice now two things that have happened. Firstly, that the relative power output has decreased. It's about 1.5 to 3. Now the 3 is kind of an overlap in two things. One, you might have a relative contribution in terms of power of 3 for somebody who's got a very well developed glycolytic system, but also the fact that as we start to transition from PCR into glycolysis, you'll get an overlap in terms of the power output. It won't suddenly just decrease. Secondly, notice though that the capacity is almost double. In fact, it is over double for energy that's derived from glycolysis. So you're generating half the power, but you're probably going for twice the amount of time, or have twice the capacity, to be able to do the work. So that's quite important. So we're seeing here the association between power and time. And this is a fundamental component that we've dealt with previously. We've looked at force velocity curves previously, we've looked at force time curves in other modules. So all you've got to remember is that if we're deriving from high energy phosphates, the ATP-PC, you can produce a very high power output. So think about the fact that the muscle can generate high forces, but it can only sustain that for a short period of time because the amount of available substrate is limited. If we now come into using glycogen, I can probably maintain a power output that is half of what we were seeing through the ATP-PC, but I can sustain it have capacity to go or sustain this for twice as long. If we then move into aerobic metabolism, which we will be touching on certainly today in the session, but not as much as we've perhaps done in other modules, you can see that through the breakdown of glycogen, the net product with CO2, so this is going through the tricarboxylic acid cycle. Notice now that actually we've gone down even more in terms of the power. We've moved from about 1.5 to 3 to about 0.5 to 0.75. In fact, we've gone down from about a third across the range here. So it's quite a significant reduction, a third to about a quarter to what we were seeing previously. But the difference is in terms of both glycogen and fatty acids. If you look at fatty acids, we've gone down even further, 0.24 to 0.4. So the power output is significantly lower, but actually the limitation really is within itself. In other words, just how much of this you kind of have got. It's almost unlimited, particularly with fatty acids. I mean, if you imagine that the general consensus is ATP-PC, you've got enough around about 10 seconds, enough ATP for a single muscular contraction. Glycogen, if you're just using substrate level glycogen under glycolytic conditions, probably enough for 60 to 90 seconds. If we're looking about intramuscular stores of glycogen and glucose, maybe 90 minutes. If we're getting up to fatty acids, you're looking at about 96 hours. But you can see that the relative power output is significantly different between using ATP-PC and energy that's derived from fatty acids. So this is really important for us because it really does set in context the notion of the association between the substrate that we're using, the amount of power that can be generated at the muscle, and the capacity that muscle has to sustain that work.